Hello everyone. In this lecture I will continue from where we had stopped in the previous lecture. In the earlier lecture I had given a brief introduction to eigenvalue problems. So here we'll take this a little bit forward using an example problem. Just to recap, a real square matrix A, it is called symmetric if its transpose is equal to matrix itself. That is, if you take the individual elements of the matrix by swapping the indices, and the elements remain the same. The values of the elements remain the same. So again, a real square matrix is said to be skew symmetric if the transpose is equal to the negative of the matrix itself. That is, if you swap the indices, then that is equal to minus of the element with the indices the other way around. And this same real square matrix is said to be orthogonal if the transpose equals its inverse. There is also a elementary theorem from maybe I think from your higher secondary school, which you might recall. That is, any real square matrix can be written as a sum of a symmetric matrix and a skew symmetric matrix. And these symmetric and skew symmetric matrices can be obtained using the given matrix as well as its transpose. Then there are a couple of theorems which are useful, especially when you're trying to solve objective questions. First one is the eigenvalues of a symmetric matrix, they are always real, and the eigenvalues of a skew symmetric matrix, they are either pure imaginary or they are zero. So now let's go to this specific problem. This is an eigenvalue problem. The problem is, suppose I have a 2D potential. I have a 2D potential V of xy. So V is so that means this is a function of x and y. So we have the x and y plane. So over there V is equal to x square minus root 5 xy plus 3y square. And that denotes an ellipsoidal basin with V minimum at 0, 0. So if you substitute x equal to 0 and y equal to 0, so we have 0 here, 0 here, and 0 here. So V minimum, the value of the minimum potential is 0. So we need to find out the positions, that is, if there are any positions, such that if you release an object, if you release a particle, then the particle will aim towards V minimum, and if it crosses V minimum, it is going to perform simple oscillatory motion. So to visualize this, we have to think of a basin which is elliptical in shape. So something like this. So let's say I have a basin, so something which is like, if I take a cross section of the basin, it is elliptical, then the size of the ellipse gets smaller and smaller and smaller. I think I should do it slightly differently. So something like this. Yeah, it looks kind of like a bowl. Okay, we're talking about basin here. Okay, so the cross section is basically elliptical. Then the minimum occurs over here. This is where the minimum is. It occurs at x equal to 0, y equal to 0. So this is how you can visualize. So the origin, okay, it touches the origin over here. So x equal to 0, y equal to 0. So this is the x-axis and this is the y-axis. So this is the elliptical basin. So every ellipse that I draw here, that represents points with the same potential. So we need to find out those places. Okay, we need to find out those positions, such that suppose I have an object, so I take a particle over here and I release this particle. This particle is going to aim its motion, it will be aimed towards V minimum. It will cross V minimum, go on to the other side, again it's going to come back, okay, and it's going to perform oscillatory motion like this. Okay, so this is basically the problem that we are trying to solve over here. So let me just grab this and place this over here. So this is the exact same problem. So I'm going to write this potential in general. I'm going to write this in this specific form. We will see this. This is actually what is called as a quadratic form. We will see that later. So v is equal to ax square plus bxy plus cy square. So such a form, it eventually it's going to help us to find out the eigenvalues. So v is equal to ax square plus bxy plus cy square. So I write it in general like this. And here when we compare this with the potential which is already given, we immediately can see that a is the coefficient which is multiplied with x square. So a in this case is equal to 1. B is the coefficient of xy, the cross term. So in this case b is going to be equal to minus root over 5, and c is the coefficient of y square. So c in this case is going to be equal to 3. So we need to find out the force. Because if I want to aim this trajectory, if I leave a particle on this ball, like if I go back here, if I take the particle and place it over here, its motion is going to be determined by the force that is acting on this, and the force that is acting on this is going to depend on the potential. Okay, and how does force depend on the potential? It depends like this: force is equal to the negative gradient of the potential. So we'll do there's a contour diagram of this same situation over here. This is from the top view, so I have tried to make a three-dimensional representation of the problem here. So this is basically the top view. Okay, so we are having, so each of these ellipses that you see, these are the contours. That means each of this ellipse, so suppose I take a point over here and a point over here, all the points which lie on a certain ellipse, all of those points will have the same value of v. Okay, so the locus of all points with the same value of v, they are going to trace out an ellipse. So we are looking for those positions. So let's say this red position that we have here, this red position, this is a position from where if I keep an object over here, it is going to aim this towards the v minimum. So this is the v minimum, which in this case happens to be at the origin. So this is the v minimum. V minimum is over here, it's at the origin. So if I keep this here, it's going to aim towards this origin. Okay, and then it's going to keep on oscillating, it's going to keep on crossing the origin. If I keep it at some other place, then it's going to perform some much more complicated motion. Okay, but there are only certain places where if I keep it, it's going to perform oscillatory motion, simple harmonic motion. Okay, so we are interested in finding that. So this basically is the problem. So for that I need to know what is the force. Okay, so let me just zoom in a little bit. Okay, so I have the object over here, and when I release this from here, it will be acted upon by some force, and that force, we want that force to be directed along this in this direction, because that's the way the force is going to be. The force is going to direct the particle towards the v minimum. So the force is going to be something like this. So this will be the direction of the force. Okay, so that's the force right there, the force vector. The force vector F. This is a force vector, it should be in this direction. So the force is equal to negative gradient of the potential, so that we already know. So from here we can find out the components of the force. So we can get the x component. So x component is simply the negative of the partial derivative of the potential with respect to x, and from here, if this is the v, you take the partial derivative with respect to x, that is going to give us minus twice ax minus by, and similarly fy is the negative partial derivative with respect to y, so that is minus bx minus twice cy. Okay, so now I want the force to be directed towards v minimum. So what is the condition here? If we want this to happen, if you want the force to be directed towards v minimum, the condition must be this: f of x by f of y must be equal to x by y. So this two must be proportional, and you can easily see this over here. Let me again zoom in. You can see this over here. So if this is the force, okay, if this is the force, then this will be the x component of the force. Oops. So this will be the x component of the force. Okay, and this will be the y component of the force. So this is, sorry, this is a y, this is a y component, this is the x component. So this is the x component fx, and this is the y component fy, and you can see from here that this forms a similar triangle. So you can see it like this. So we have like this. This is the direction in which I want the force to be directed. So this is the point, the particle is over here, the particle is over here. So this is your x, the x coordinate, and this is the y coordinate, the x and the y coordinate of the particle. You want the force to be directed towards this. So this force will have a x component, this is fx, and similarly we'll have the y component fy. Okay, so these are two similar triangles. These are similar triangles. So from here we get this particular ratio. Okay, so f of x by f of y, it must be equal to x by y. So this we call as equation number 1, and this one we call it as equation number 2. So now equation number 1, that is this equation, can be written, you can easily see, it can be written as a matrix equation like this. You can verify for yourself. So if I multiply this matrix with this matrix, so we have minus twice ax minus by, which is equal to f of x, which is the first equation. Then we have minus bx minus twice cy is equal to fy, which is the second equation. So this equation can be written as a matrix equation like this, or very simply we can write it as, okay, sum matrix f, small f, is equal to sum 2 cross 2 matrix. This is a column matrix, small f, is equal to a 2 cross 2 matrix H times another column matrix R. So over here the components of this F is equal to Fx and Fy, and the components of this R matrix is X and Y. Okay, so now equation number 2, so this particular equation, this equation, it implies that this X component is proportional to, X component of the force is proportional to the X coordinate, and the Y component of the force is proportional to the Y coordinate. So which means the force is proportional to its position vector. The force is proportional to the position vector. So F is equal to lambda R. Okay, so F is equal to lambda R. So here at this point I'd like to make a prediction. The prediction is, because you see this lambda is going to turn out to be the eigenvalue. Okay, let me just finish that step, then we'll make the prediction and see whether it comes true or not. So we have F is equal to lambda R, okay, because F is proportional to R. The components of the force is proportional to the coordinates. Okay, so F is proportional to R. So therefore F can be written as some constant into R. So now from equations 3 and 4, from this equation, equation number 3 and equation number 4, this is what we get. HR is equal to lambda R. HR is equal to lambda R. So H is a 2 cross 2 matrix, R is a column vector, lambda is a scalar, and again this is the same column vector. So this is nothing but a eigenvalue equation. Okay, of course here I just wanted to clarify here what is this small f, this f, this column vector f is of course this H is this, and this R is this X and Y vector. So here this one is, as you can see here, we can immediately identify this is an eigenvalue equation, and this needs to be solved. So now I'll make a prediction here. The prediction here that I'll make here is this lambda is going to give me the eigenvalues. Here we expect 2 eigenvalues. Okay, we expect 2 eigenvalues over here because it's a 2 cross 2 matrix. It's a square 2 cross 2 square matrix. So we expect 2 eigenvalues here, and I'm predicting that both the eigenvalues will be negative. How do I know that? Okay, how do I know that? We know it from here, just by looking at this diagram. You can see here the position vector. What is the direction of the position vector? The direction of the position vector is always from the origin till this point. This is the direction of the position vector. Okay, so this is the direction of the position vector. So position vector and the force, they are opposite to each other, and in fact that's what should happen. If you want simple harmonic motion to take place, then the force is always opposite to the displacement, and it is proportional to the displacement. So that gives rise to the restoring force. So force is opposite to the the force is going to be opposite to the position vector. So the whatever eigenvalues we get, when we solve this, we can expect both the eigenvalues to be negative, and let's see if that really happens. Now in this equation number 5, this is the eigenvalue equation which needs to be solved, and over here H is a known matrix and lambda and R are the quantities that we need to determine. I mean, that's basically what an eigenvalue equation, solving an eigenvalue equation, basically that's what it entails. So H is a known matrix which we all know here. H is known, so twice A, B and C, these are the quantities which are already known to us. It's known to us from the form of the potential. Okay, from the form of the potential we know that what is A, B and C. So from there, if you know A, B and C, you know what is H. So H is a known matrix and lambda and R are the quantities that we need to find out. So doing that, straightforward. So from this equation, equation number 5, we take this lambda R onto the other side, and the lambda I multiply with the identity matrix. So we have H minus lambda into identity matrix times R is equal to 0. We'll call this equation number 6. Then this equation number 6 will have a unique non-trivial solution if the modulus, this particular modulus is 0. The determinant of this matrix H minus lambda I, this determinant is equal to 0. So over here we have this components of this H is H11, H12, H21, H22. Of course, we know what is H. We know this H11 is equal to minus twice A, H12 is minus B, H21 is minus B, and H22 is minus twice C, which is written over here, which is clarified over here. So H11 is this. Okay, so this is the matrix. I'm just writing this just to be able to get a generic expression. So that's why I'm writing these in as the components of this matrix H. So now when you evaluate this determinant, so you'll get H11 minus lambda. So this into this, we are basically doing this kind of operation. So we go like this, right? There's a minus sign here, so this into this minus this into this. So doing that, we get something like this, and now it's just a matter of substituting the H11, H12, these components. So H11 is minus twice A, so minus twice A minus lambda. H22 is minus twice C, so minus twice C minus lambda. So H12, H12 is minus B, H21 is also minus B, so minus B into minus B, which is equal to 0. And if you simplify this, I'll leave this to you, you will get something like this. Okay. So this in either of these equations, equation number 7 or equation number 8, either of these equations are known as the characteristic equation for H, and the left hand side of this characteristic equation is known as the characteristic polynomial. So this is a polynomial that we have here on the left hand side, so that is known as the characteristic polynomial. So now this is this equation number 8, that is equation number 8. We'll just take this over here, equation number 8. That's the characteristic this characteristic equation. So again, just a recap, V is given as this in the problem. So A is equal to 1, B is equal to minus root 5, and C is equal to 3. So we can just substitute A, B and C in equation number 8, and when we do that, this equation number 8, this is going to become this. So lambda square plus 2 into A is 1 plus C is 3. So 1 plus C, 1 plus 3 minus, okay, this b square is minus root 5 square is going to be equal to 5 minus 4 into 1 into 3, 4 into 1 into 3, which is equal to 0. So this is going to give us, you can factorize this, and you can get this as lambda plus 1 into lambda plus 7. So this gives us the eigenvalues. The eigenvalues are minus 1 and minus 7. So why are we not surprised? Because this is a prediction that we already made. The prediction was that both the eigenvalues should turn out to be equal to minus 1. It would have been surprising if one of the eigenvalues was plus 1 positive and the other one was negative. That would have been surprising, because that would have indicated that the restoring force, it is not opposite to the position vector, it is actually in the direction of the position vector. So that would not work. That will be an unphysical scenario. Okay, so what we are doing, so it means this tells us, this is encouraging, it tells us that we are going in the right direction. Okay, so for so all we need to do is find out the eigenvectors, that's all. So we can find out the eigenvectors for the corresponding eigenvalues. So eigenvalue lambda is equal to minus 1. So let's take lambda equals minus 1. Then equation number 6, where is it? I think it's in the previous slide. Equation number 6, this is equation number 6. So we'll substitute lambda is equal to -1 over here. Okay, so this is equation number 6. So lambda equal to, so h, substitute the components, h minus lambda, okay, h11 minus lambda, h22 minus lambda, and the other two components, they remain the same. So lambda is equal to -1, okay, into xy is equal to 0. And from here, -2 minus -1 is going to give us a -1, and -6 minus -1 is going to give us -5. So we get this one. So this multiplied with this is equal to 0, that is going to give us one equation, and this into this is equal to 0 is going to give us another equation. So these are the two equations which actually turn out to be the same, the one and the same, because if you cancel out this √5, so both of them are going to be exactly the same. So it gives us that x is equal to √5y. So now for the eigenvalue, lambda 1 is equal to -1. What will be the eigenvector? The eigenvector is this one, x, it follows this relation, x is proportional to y. So if I put y equals 1, so if I put y equals 1, the value of x will be √5. So if y is equal to 1, value of x will be √5. Okay, and then I can just multiply this with some constant c1. I put a constant c1 so that it gives me the flexibility of normalizing this eigenvector whenever I want. Okay, so I can set the value of c1 in such a way that this eigenvector, it gets normalized. So this gives us the first eigenvector. So now what about the second eigenvector? In a similar way, we just substitute, instead of lambda equal to -1, you put lambda equal to -7 and work this out. I'll leave this to you as an exercise. So for this one, for the second eigenvalue, you will get this eigenvector to be equal to 1 minus √5. C2 again is a constant which I am keeping for the purpose of normalization. Okay, so these are the eigenvectors that we wanted. So this is one eigenvector and this is another eigenvector. Now these two eigenvectors, they provide a natural orientation. Okay, these provide natural orientation directions along the ellipsoidal basin. Okay, so these R1 and R2, these two vectors R1 and R2, they describe what are known as the principal axis. So you can see that from this diagram. So if this was the ellipsoidal basin, then this will be the direction of R1. You can check for yourself. R1, x is √5 and y is 1. So both are positive. So R1 will be in the first quadrant. So √5 is greater than 1. So the x component will be more than the y component. So it will be this will be a direction of R1. What about R2? X is positive, y is negative. It has to be in the fourth quadrant. So x is positive, y is negative. And over here, the y component, its magnitude is more than the x component, so it will be something like this. So this is your R1 and R2, and this R1 and R2, I could take another set of axes. Along R1 and R2. I could take another set of axes. So this axis, this is along R1 and this is along R2. This axis along R1 and R2. And this is the original axis that we have. So this new axis, it gives us a much more natural orientation direction in order for us to analyze this particular problem. So that's why these are known as principal axis. So this was a problem that I wanted to solve in this particular lesson. In the next lesson, we will study what is known as orthogonal transformations. Thank you.